Now, choose important features of the motor that would be required for continuous operation using AC or DC power, not and choose one. I mean, choose AC or DC. You don't need to choose me about both. Tell me about both, rather. Now, the important thing about this question is that it is asking you for features of the motor. So we're asking for things that are part of the motor, not that are to do with the power supply. Now, they're going to depend on the power supply, but they've actually got to be part of the motor. So let's start off with AC. Now, in order to use AC power, we would need slip rings. Now, why do we do that? Because they provide a constant connection. And I would say that the AC changes direction every 180 degrees, and that allows for continuous rotation. So this is an explanation, excuse my scribbly writing, that describes a feature of the motor and explains why that works. Now, if we were using DC, then we're going to be talking about split rings or a commutator / commutator. Now, now it is a slightly different answer because it's actually saying that the split ring changes the direction of the current. But then a lot of the answer is actually pretty similar. So you're going to say the split ring changes the direction of the current every 180 degrees, allowing continuous rotation. So the main thing is that you have the correct things grouped together. So AC goes with slip rings and DC goes with split rings or a commutator, but you also need to provide a brief explanation as to why they are used. Okay, question 9. The motor is now used as a generator. It's rotated with a frequency of 120 Hertz and calculate the magnitude of the EMF of the coil. Now, all the information's been given previously, so we've just got to apply this to the question. Now, all I'm really looking for in this question is that you're using the total EMF is negative in, well, actually don't even worry about the negative sign so much. The number of turns times the change in flux over the change in time. So you can use the other formula if you want, and you'll get a different result, which is also accurate. But this is an acceptable way of doing it. So all we've got to do here is think about the change in flux. Now the change in flux is equal to, I'll just write that over here, change in flux is equal to BA, which is 0.45 times 0.012, and that was 5.4 times 10 to the minus 3. And our delta T is 1 over 4F. So it's 1 over 480 seconds. So then we just got to put these in. 5.4 times 10 to the minus 3 over 1 over 480, or you can just do 480 to the minus 1. Oops, I should have done multiplied by 500 first. And then we get, so it's at 1296 volts. Now remember significant figures again. The least significance that I've given you here in anything is 2, so that's going to round to 1300 volts. If you use the other formula, you would have found that the maximum EMF was very close to 2000 volts. Okay, sketching the waveform of the coil. The waveform in the coil. This is important, because the waveform in the coil is always AC. We can do things to change that outside the coil, but in the coil it's always an alternating potential because of the rotating motion. Now, what have we got here? We've got our EMF in volts, we've got time in seconds. Now, what do we know? The only thing we really know is that this is 1/120th of a second, which is 0.0083 seconds, or something like this. If you did the other equation, you've calculated the maximum EMF at 2000, so you could actually write 2000 here. I'm not so fussed about that one because not everyone's going to use that approach. You can't write 1300 volts as the maximum voltage because that's definitely not right. So the main thing is a correctly labeled graph with a sine wave form and labeling the time position there. Okay, now question 11. This was quite badly done. So the understanding of Lenz's law is clearly not really where it needs to be. Now this is purely a qualitative question here. There's some numbers I've thrown in that are not actually relevant to this question. I think I was just being, cheeky or whatever. All you've got to think about is what's happening. So we've got a cannonball that's falling, and it is falling north first, so north first, and it's falling into a loop. Now, that's a terrible loop. Now, imagine this is the front of the loop here, and this is the back of the loop here. Now, when it's falling in, what's happening is that the flux is increasing in this direction. Now, what that means is that the flux from the induced current is going to be resisting it by coming up in this direction inside the loop. Now, if you think about that, that means it's going to be going down the outside of the loop and up the inside like that. Now, if you now, the first thing to do that I'd suggest is you can apply the left-hand rule. So this is my rule for predicting the direction of the current. Now, if you get your left hand and point it with your thumb down, what you're going to see is that your fingers are actually going to be going in an anti-clockwise direction around here when you're looking from above. So immediately we should know that the direction that we're rotating in is actually an anti-clockwise direction. Now, so we've got anti-clockwise. Now, if you don't use the left-hand rule, that's fine, because you should end up with the same answer anyway if you use the right-hand grip rule. Now, you need to put your fingers around an imaginary wire so that your fingers are pointing in the direction of the arrow. Now, this is with your right hand. Now, what you'll find is that your finger, or your thumb rather, sorry, will be pointing around the circle in an anti-clockwise direction, exactly like the green line that I've already drawn. Now, understanding the right-hand grip rule is important because that's the explanation you need. So, what you need to do to actually explain this one is to say that, so according to Lenz's law, try and spell that correctly, the flux from the induced current is will oppose the change in flux. Now, at times I've talked about external flux, and that's something that you see written in some questions. At least I think I didn't just make it up. What we mean by that is the flux that is coming from the external source of the magnetic field, which is the magnet. So we're opposing that change in flux. Now, the change in flux is down through the loop. Now, what that means is that the opposing flux must be up, must upwards, and then from the right hand grip rule, we know that the current is anti-clockwise. Sorry, that's barely speaking English. Alright, sorry that's a bit of a mess, but I hope you see the idea here that we need to do to answer this sort of question properly. So one, you've got to figure out the direction. Now, it doesn't matter how you do that. The left-hand rule is good because it's quick, and as long as you understand the direction the flux is going or changing in, you'll get that right. Then what have you got to do? You've got to refer to Lenz's law, you've got to describe what's happening with the flux, and you've got to link it, use the right-hand grip rule to explain how that relates to the direction of the current. So to answer something like this well, you've really got to think about 3 or 4 things to do it.